to exploring the quantum computing future that we're creating right now. And it is a real pleasure to be here with all of you to discuss and explore some of the implications of this amazing technology. Let me set it a little bit on context on the institution I represent and that I lead for IBM Research. And this year is actually our 75th anniversary that we've had a research division. And at present, we have over 3,000 scientists and engineers distributed all over the world. And over our history, we've maintained always this commitment to do very fundamental investments in core science, of the type of work that have produced Nobel Prize-winning achievements, but also to explore the implications that these advancements would have to the world of information and the world of computation. Just to give you a little bit of a flavor where some of the work that I'll be sharing with you today gets carried out, this is the laboratory where I work. This is the T.J. Watson Research Lab. It's about 45 minutes north of New York City. And in the building, we have about 1,700 scientists and engineers that work here. And I'll show you also, results along the way. This is our laboratory in Almaden, in California, a little bit south of San Jose, who's on top of this beautiful state park. I'll show you just one more laboratory. This is a laboratory in Zurich, in Ruschlikon, where a lot of very fundamental physical sciences work also gets carried out for IBM Research. And I share this because, in the context of what we're going to be discussing, what we do is we attract extraordinary mathematicians and physicists and chemists and specialists in engineering and in quantum, as an example, to explore what is next. And this is the most exciting time in the world of computing in the last 50 or 60 years. And simply put, what is next is we have this intersection of technologies that are coming together and have this very simple equation to define what is happening now and what is next in computing, which is going to be this intersection of bits plus neurons plus qubits coming together. And that if we were to sort of very briefly summarize the last 50 or 60 years of information and computation, we could say something along the following lines. That we build the information technology edifice on top of the ideas of Claude Shannon that gave us what is now known as classical information theory. And Shannon is the one that taught us to think about this world of information abstractly. He told us, introduced to us the term of the bit, the binary digit, and he said, well, we could decouple in some ways this idea of zeros and ones from their physical implementation. And it's that separation that allowed us to go and see things like a punch card and DNA and come to appreciate that something as physically different as those two things had something in common, that both can be understood as carriers of information. And with this, and as a companion with Moore's law, we have built modern computing. We've digitized the world, we've made bits ubiquitous, and essentially almost free. And the situation that we now face is the consequence of the intellectual quest of a series of scientists that, beginning in the 1960s, took that very idea that Claude Shannon put forth, this separation of physics and information, and started to poke at it. They started to question whether it was really true that physics and information were separate. And I'm showing here an example of Charlie Bennett, for example, on the right-hand side, who is one of the fathers of quantum information theory. And what the physicists started on in the early 60s and 70s, they would ask questions like this. They would say, is there a fundamental limit to how energy efficient computing can be? They would ask questions whether information processing could be thermodynamically reversible. Only the kinds of questions that a physicist would ask, right, about those kinds of things. And poking down that thread, we got to understand that there is another way to understand information. And this is a photograph of a notebook from Charlie Bennett that has the words, look it up there, quantum information theory. We think it's the first time that those words were written down, and that was done in 1970 in our lab. So that's how long we've been in this journey in IBM Research exploring these ideas. And what we came to appreciate and realize based on that theoretical work is that the building block of the world of information is not the bit, the 0 and 1, but rather something known as the quantum bit, the qubit for short. And that at the heart of this idea of the qubit, we're going to bring three ideas of physics that is going to enrich the possibilities of what we understand information to be. And the three ideas are the ideas of superposition, interference, and entanglement. So let me just briefly describe what they are and why they matter. So superposition is actually very easy to understand. We have a classical analog to it. So in the classical world, we have zeros and ones. Let's say we had a coin, heads or tails. And when the coin is spinning, if I ask you, is it heads or tails, what would you say? You would say, yeah, it's a combination of heads and tails. When I perform the final measurement, I either get one position or the other. Okay, so far, so good. So now we're going to introduce the second idea. And by the way, so that idea in the quantum world for us, of the zeros and ones, is that instead of having a 0 or a 1 only, I could have a superposition, combinations of 0 and 1. The second idea is actually really profound and sophisticated, so I won't spend a lot of time, but I'll give you an intuition for it. And there's the idea of entanglement. And entangled qubits in this case have this property that it is impossible to describe the combined state independently of one another. So let's go back to our coins. So in this case, we're going to have two coins. And in classical world, if I was spinning the two coins and I perform a simultaneous measurement, whether one coin was heads or tails is independent of whether the other one is heads or tails. The probabilities are independent. In quantum world, if these coins were entangled, when I perform that measurement, now I can have situations when one is heads, the other one is always heads, and one is tails, the other one is always tails. That's one of those things that when you actually reflect on it, is one of these earth is not flat kind of moments, right? That is a really profound thing, because what it tells you is you can have non-local action in the universe. So this property, which is weird in its nature, but is something that reflects the nature of physical reality, there's a relationship between this special property and the world of information. And it's the following. If I had 100 perfect qubits that were entangled, that had this property with one another, if I try to represent all the possible states of that entanglement of those 100 qubits using bits, using zeros and ones, I would need to devote every atom of planet Earth to store zeros and ones. By the time I have a quantum computer with 280 perfect qubits, I would need every atom of the known universe to store zeros and ones. So that's a very interesting property to go and harness and see what we can do. The third principle of physics that we bring into information is the idea of interference. And this is something, again, we're all accustomed to seeing in waves in the ocean. And the idea is you can have waves that can interfere with one another and constructively add up to form, the peak of the wave. And sometimes you can cancel and they form the valleys of the waves. So those three ideas. Okay, so how does an algorithm work to just give you an intuition for how different it is than a classical computer in which you have switches of zeros and ones and you implement the basic logical operations of the ands and the ors and the nots. So, how does it work? In a quantum computer, the first thing we do is we put the quantum computer in a superposition. So let's say we have a very simple quantum computer with just 2 qubits. The number of states that is available in my quantum computer is 2 to the power n, where n is the number of qubits. So since I have 2 qubits, 2 to the power of 2 is 4. So I have a 0, 0, 0, 1, 1, 0, 1, 1 state. In this case, we're going to represent them in a sphere. So imagine that if I wanted to put a 1, I would put a dot in the north pole of the sphere. If I wanted to have a 0, I could put it in the south pole. And if I want to have a combination of 0 and 1, I would put a dot on the equator. In this case, I have 4 dots on my sphere. Each dot is represented by an amplitude and a phase. The phase is where is it in the sphere in its rotation. Okay, so first thing, that's all I do. Second thing I do is I need to put data into the computer. What it means in practice is that when we send that information into the computer, we change the phase where it is in the sphere of those dots. And here's where the special step comes in. The next step of writing an algorithm, now that I have my data into the computer, is the process of taking those states that have an amplitude and a phase and interfere them with one another, like waves in the ocean, to maximize the answers I want and cancel the answers I don't want. So here I have the possibility of playing with negative probabilities. I can cancel things out. So I can explore a sea of possibilities to find the answers I want with this process of interference. Very, very different than a classical computer. Why does this matter? This seems so esoteric and theoretical. Well, the reason it matters is because we could divide the classes of problems that we can solve in the world into easy problems and hard problems. Easy problems are ones in which the number of variables we have to compute over are not exponential. And really, that's what classical computers, all the computers we all have, are good at solving. We know there are other problems that are exponentially difficult to solve because the number of variables are exponential in nature. Examples of problems that look like that are factoring, which we use as the basis to encrypt a lot of the information in the world, but very fundamentally too, modeling nature, the process of doing chemistry and materials and understanding how nature behaves is also exponential in nature. And the thing to realize about quantum is that it's the only technology we know that alters the equation of what is possible to solve versus what is impossible to solve. I'm not making the claim that all hard problems will be able to be solved with quantum computers. But I am making the claim that it is impossible to solve those hard problems with just classical computers. So that's really important and powerful. So can you build these machines? I made the claim that this is the most exciting time in computing in many decades, so it's useful to go back to this moment. So this is 1944. This is the first programmable computer that was built at Bletchley Park. And in some ways, we're in a similar moment, where the first programmable quantum computers have been realized and built. And this doesn't happen that often, right? And it's very, very exciting that we find ourselves in this moment. And inside it, there's different ways to build these quantum computers. In our case, we use superconducting technology based on a device called the transmon qubit. And what we have in the end is we have a device that is about 100 nanometers in dimension. It's a Josephson junction, and it's a sandwich of aluminum and aluminum oxide. And basically, we are able to create the equivalent of an artificial atom that creates a ground state and an excited state. And what you're seeing in here is that that device, each one of those squares represents a qubit. And you see these wiggly lines that connect qubits to one another. And that is what allows us, through these coupling resonators, to build this superposition and entangled state between different qubits. So in the end, we're using silicon technology that we have benefited from decades of investments in semiconductor technology and create a new device and a new capability to be able to create these quantum bits.